Suppose I told you that no matter how smart you get, and I mean smart, not just human smart, I mean civilizations that have been around for 1 billion years smart, civilizations with computers the size of solar systems, with every atom in a galaxy harnessed to do nothing but calculate, suppose I told you that even they cannot predict where a single electron will be 1 second from now. Not because they're lazy, not because they forgot to carry a decimal, but because the universe itself, at the deepest level you can dig to, refuses to be pinned down. Now, you're sitting there thinking, that's just because we're limited. That's a technology problem. Give us enough sensors, enough computing power, enough time, and we'll figure it out. And I understand why you think that. It's a perfectly reasonable thing to think. It's also completely, spectacularly wrong. And the reason it's wrong is one of the most beautiful things I have ever encountered in my life in physics. Let me start somewhere simpler. Let me start with a billiard ball. You've seen a billiard ball. Round, smooth, you hit it with a cue, it goes somewhere. Now imagine you want to predict exactly where that ball will be after bouncing around a billiard table for, say, 1 minute. Sounds like a job for Newton, right? Forces, velocities, angles of reflection. We've been doing this since 1687. So you set up your equations, you measure the position of the ball very, very carefully. You measure its velocity. You run the numbers. Here's the catch. In order to predict where that ball is after 1 minute of bouncing, you need to account for the gravitational pull of every object around it. The table, the room, the building, the earth, the moon, the Sunday. These forces are tiny, unbelievably tiny, but they accumulate. And here's what somebody actually calculated. It was done by the physicist Michael Berry. And when I first heard the result, I had to sit down. If you ignore the gravitational pull of a single electron sitting at the edge of the observable universe 10 billion light years away, your prediction of the billiard ball's trajectory will be completely wrong after just 56 collisions, 56 bounces, and 1 electron 10 billion light years away has already ruined your calculation. Now you see the problem differently, don't you? This isn't a failure of intelligence. This isn't a failure of effort. This is a property of a certain class of mathematical systems called chaotic systems. And it says that tiny differences in your starting information grow exponentially over time. The technical term is sensitive dependence on initial conditions, but I prefer to call it what it is. The universe's way of telling you that your measurement was never perfect enough, and it never will be. But wait, I'm getting ahead of myself, because what I just described, the billiard ball problem, is still a classical physics problem. It says you need infinite precision in your measurements, and since you can't achieve that, you lose predictive power. A sufficiently advanced civilization might argue, fine, we'll just measure more precisely. We'll measure position and velocity to 1 trillion decimal places, a quadrillion, as many as you like. The principle in classical physics doesn't say you can't measure that precisely. It just says that whatever precision you achieve will still not be enough if you wait long enough. That's already a profound limitation, but it's not the deepest one. The deepest limitation comes from quantum mechanics, and it has a name that everyone has heard and almost nobody has sat with long enough to really feel: the Heisenberg Uncertainty Principle. I want you to hear this not as a textbook sentence, because it always gets mangled in textbooks. It comes out sounding like, you can't measure position and momentum simultaneously. And people nod and think, oh, it's a disturbance problem. When you look at an electron, you bounce a photon off it and knock it around. Measure more carefully, use a gentler photon, and you do better. No, that explanation is wrong. Not slightly wrong in a way that misses the entire point. Werner Heisenberg discovered something far stranger and far deeper. And if you'll give me a few minutes, I'll show you what it actually is. Here's the real situation. Position and momentum, the how fast and which direction of a particle, are not two separate properties that happen to disturb each other when you measure them. They are, at a fundamental level, conjugate quantities, which means they are connected by the mathematics of waves in a way that makes it literally impossible, not just practically difficult, for both to have definite values at the same time. Think about a wave on a string. If I shake one end of a string and create a wave, that wave has a wavelength, a distance between peaks. Now, a particle's momentum, according to quantum mechanics, is directly related to its wavelength. High momentum means short wavelength, low momentum means long wavelength. But here's the thing, to have a well-defined wavelength, you need a long wave. You need many, many oscillations stretched out over a large distance. The more oscillations you have, the more precisely you can identify the wavelength and therefore the momentum. But a long wave spread over a large distance is a wave that's everywhere. It doesn't have a location. You cannot say that wave is here. It's here and here and here and also there and over there and a bit over there too. To localize a wave, to make it be somewhere, you have to add up many different wavelengths together. This is called a wave packet. You pile up waves of slightly different wavelengths and they reinforce each other in one region and cancel each other out everywhere else. The more waves you pile up, the more precisely localized the packet becomes. The more tightly you confine the position, the more wavelengths you need, and the more spread out the momentum becomes. This is not a measurement problem. This is not a technology problem. This is a mathematical feature of waves themselves, and particles, all particles, the electrons in your body, the atoms in your brain, the quarks making up the protons in the nuclei of every atom in this room, all of them are described by these waves. This is what they are. Not because we haven't understood them well enough yet, because that is the nature of the thing. And now I want you to feel something. Because what Heisenberg's equation actually says, delta x times delta p is greater than or equal to h bar divided by 2, what this equation says is that there is a minimum amount of combined uncertainty in position and momentum, and it is set by a constant of nature, Planck's constant, h bar. This number, 1.055 times 10 to the minus 34 joule seconds, is written into the structure of the universe. It does not care how smart you are. It does not care how many telescopes you have. It is not a placeholder waiting to be improved upon. It is a fundamental feature of reality. Now, our hypothetical alien civilization has run straight into this wall. They build their machines. They design their instruments. They cool their detectors to within a whisker of absolute zero to eliminate thermal noise. They use quantum computers of a sophistication that makes our most powerful devices look like an abacus. And they sit down to predict the position of a single electron in their laboratory 1 second from now. They cannot do it, not because of engineering limitations, because the electron does not have a definite position 1 second from now. It has a probability distribution, a smear of possible locations. The wave function of the electron evolves in time, according to Schrödinger's equation. That part is perfectly deterministic. That part they can calculate exactly. But when you ask where is it, the answer is genuinely, actually, irreducibly probabilistic. And when you make a measurement and the electron appears at one specific location, the other possibilities don't get realized somewhere else. They simply were never definite. The electron was not secretly at that location all along, waiting for you to look. It was in a superposition. It was, in a precise mathematical sense, in multiple states simultaneously, until the interaction with a measuring device forced an outcome. I can see some of you shifting in your seats. Some of you want to argue with me. Good, you should. Because this is deeply counterintuitive, and your discomfort is the right response to a genuinely strange fact. Some of the greatest physicists who ever lived felt that same discomfort and could not accept it. Einstein could not accept it. He spent years, productive years, brilliant years, but also frustrating years, trying to show that quantum mechanics was incomplete, that there were hidden variables underneath, a deeper layer of the theory where things were still deterministic and exact, and that the probability was just our ignorance showing through. He said the theory was correct but incomplete, the way a weather forecast is correct in a statistical sense, but incomplete because it doesn't tell you the exact trajectory of every air molecule. In 1935, Einstein, together with Boris Podolsky and Nathan Rosen, wrote a paper that they thought demonstrated this incompleteness, what we now call the EPR paradox. They showed that quantum mechanics, if taken seriously, predicted correlations between separated particles that seemed to require either faster-than-light communication or the existence of those hidden variables that Einstein preferred. It was a beautiful argument. It was also, as we now know, the setup for one of the most remarkable experimental confirmations in the history of science. In 1964, John Bell, a physicist at CERN, who worked on accelerator design by day and thought about foundations of physics by night, wrote down an inequality, a mathematical test. He said, if there are hidden variables, if the probabilities in quantum mechanics are just our ignorance of deeper real values, then experiments on correlated particles must satisfy this inequality. If quantum mechanics is really telling the truth about reality being fundamentally probabilistic and non-local, then the inequality will be violated. In 1972, John Clauser performed the first real experimental test. Then Alain Aspect, in the early 1980s in Paris, performed better experiments with stricter controls, closing loopholes one by one. Aspect won the Nobel Prize for it in 2022, and the result? Quantum mechanics wins. Bell's inequality is violated. The correlations between particles are stronger than any hidden variable theory can produce. The universe is not deterministic underneath our ignorance. The probabilities are real. Einstein was wrong. I say that without any pleasure in proving a genius wrong, because Einstein was right about so many things, and his concern came from a deep physical intuition that demanded a coherent underlying reality. But the universe, it turns out, is under no obligation to satisfy our intuitions. And when experiment speaks, we listen. That is what science is. Now, here is where things get even more interesting, because we haven't hit the bottom yet. We've discussed chaos, the exponential amplification of tiny errors in classical systems. We've discussed quantum uncertainty, the fundamental indefiniteness of particle properties at the quantum level. But there is a third limit, and it's the strangest one to me, perhaps because it feels like something a philosopher would say rather than a physicist, except it turns out to be the most practically concrete of all. It's called the limit of computability. Imagine our alien civilization decides to sidestep the quantum problem by doing something clever. Instead of trying to predict individual particles, they're going to simulate the entire quantum wave function, all of it, for the whole universe. They're going to build a computer, a truly extraordinary computer, a computer made of the matter of an entire galaxy, the most powerful information processing device that physics allows, and they're going to run the universe's wave function forward in time and read off what will happen. Here's the question I want you to think about. How many bits of information do you need to simulate the observable universe? The physicist Raphael Bousso and others have worked out, using the mathematics of black holes and thermodynamics, that the observable universe, the part we can see, can contain at most about 10 to the power of 122 bitses of information. That's a big number. I won't pretend it isn't a big number, but it's finite. And here's the killer. In order to simulate a system, the simulator must contain more information than the system being simulated. You cannot perfectly simulate the universe on anything smaller than the universe itself, and even then, there are deep mathematical problems with that idea. But let's ignore that for a moment and give our aliens the whole universe to play with. Let's say they're willing to convert the entire observable universe, every star, every planet, every nebula, every dark matter halo into a computer. Maximum possible computation. What does this computer get them? It turns out that even using every particle in the observable universe as a computational resource, running at the maximum possible clock speed allowed by quantum mechanics, the Planck time, which is about 5 times 10 to the minus 44 seconds and running for the age of the universe, you get a computer that can perform roughly 10 to the power of 123 elementary operations. That's a lot of operations. But the complexity of quantum systems grows exponentially with the number of particles. Simulate a system of n particles, and the computational resources needed scale as 2 to the n, or worse. For a macroscopic object, say, a single grain of sand with something like 10 to the power of 19 atoms, a perfect quantum simulation would require more computational resources than our entire alien galaxy computer has. A single grain of sand defeats the most powerful computer a civilization could possibly build. I love this result. I love it because it's humbling in the best possible way. It doesn't say, we are stupid. It says the universe is bigger than any container you try to put it in. Every attempt to grasp it completely bursts the container. But I should be careful here. I want you to see what this does not say, because there's a mistaken conclusion lurking nearby that I want to head off. None of this means science is futile. None of this means prediction is impossible. None of this means we might as well go home. Because here's what I've watched science do in my lifetime. What I've watched it do for centuries before me. Science doesn't try to predict everything. Science identifies the patterns, the regularities, the structures that repeat, and in those structures, it finds something extraordinary. It finds that even in an irreducibly probabilistic, chaotically sensitive, computationally intractable universe, there are islands of order. There are things you can say for certain. You cannot predict exactly where a given electron will be. But you can calculate the energy levels of hydrogen to 10 decimal places, and they match experiment to 10 decimal places, because those energy levels come from the structure of the wave function averaged over all positions. The uncertainty washes out into a beautiful, precise result. You cannot predict when a single radioactive atom will decay, but you can predict with extraordinary precision that if you have 1 trillion atoms, half of them will decay in exactly such and such a time. The statistics are precise, even though the individual events are not. You cannot predict the weather more than a week or two ahead. But you can understand climate, the long-term statistics of weather, because the chaotic fluctuations average out over time and space into patterns that are real and calculable. The universe is not a clock. It was never a clock. The dream of Laplace, the French mathematician who said that a sufficiently powerful intelligence, knowing the position and velocity of every particle, could calculate the entire future and past of the universe, that dream is dead, killed by experiment, killed by mathematics, killed by the universe's own refusal to cooperate. But the death of that dream did not kill science. It transformed science into something more honest, more subtle, and I would argue more beautiful, because a clockwork universe would be boring. If you could, in principle, calculate everything, then everything is already determined. The future exists, complete and fixed, and you are merely reading it off a tape. Where is the discovery in that? Where is the surprise? The universe we actually live in, the quantum, chaotic, computationally infinite universe, is one that genuinely makes things up as it goes. Not randomly in the sense of purposelessly, but randomly in the sense that the future is not written anywhere waiting to be read. It is created at each moment by interactions, by measurements, by the irreversible act of one thing touching another. And that means that when something surprising happens, when a mutation occurs, when a star explodes, when a human being has an idea, it is genuinely new. It was not implied with perfect logic by the state of the universe 10 billion years ago. I find that astonishing. I find it freeing. Do with that what you will. Now let me take a step back and look at this from a bigger angle, because I've been talking about fundamental physics, and I want to show you that this isn't just a physics problem. It's a problem that appears everywhere, in every domain where you try to predict complex things, and understanding why it appears everywhere traces back to exactly the physics we've been discussing. Consider economics. People have been building models of economies for a long time. They write equations, they fit parameters, they run simulations, and they are famously terrible at predicting what the economy will do over a period of years. Why? Is it because economists are stupid? Some of them, sure, but as a profession, no, there are brilliant people working on these problems. The reason is that an economy is a chaotic system made of millions of interacting agents, each of whom is themselves incredibly complex, each of whom changes their behavior in response to predictions about the economy, so that a good prediction, once published, changes the behavior it was trying to predict, which invalidates the prediction. This last part, agents responding to the model, is a feature you don't encounter in planetary orbits. The planets don't read the ephemeris and decide to go somewhere different, but humans do. This is called the Lucas critique in economics, after the economist Robert Lucas, and it's one of the reasons macroeconomic forecasting is so difficult. The act of modeling changes the thing being modeled. The universe, it seems, has a taste for self-reference. Or consider biology. A living cell is an enormously complex dynamical system. The number of chemical species interacting inside a single cell is in the thousands. The interactions between them form networks of feedback loops of staggering complexity. You can model parts of this system beautifully and precisely. Enzyme kinetics, signal transduction pathways, gene regulatory networks, these are understood in considerable detail, and the understanding is genuinely predictive within its domain. But predict the full behavior of a developing embryo from the physics of its initial cells, predict exactly how a particular cancer will respond to a particular drug for a particular patient. These questions are orders of magnitude beyond what we can currently do, not just because of our ignorance, but because the system's complexity puts it in the same category as our alien civilization's grain of sand. And yet, and here's the thing I want you to hold on to, medicine works, biology works. We have vaccines, antibiotics, surgical techniques, genetic therapies, all built on knowledge that is partial, approximate, statistical. The knowledge is real. It's just not omniscient. This is, I think, the deep lesson that physics teaches us about knowledge itself. Perfect accuracy is not the standard by which we should judge understanding. It is not the standard we need. It is not even in principle achievable, not by us, not by anyone. The standard for good science is something else. It's whether your model captures the essential structure of the phenomenon well enough to be genuinely useful, whether your predictions are calibrated honestly to their actual reliability, whether you understand the limits of your knowledge as clearly as you understand the knowledge itself. Knowing what you don't know is not a failure. It's a prerequisite for knowing anything at all. I want to tell you about a moment in my own experience that brought this home to me in a personal way. When I was working on the theoretical aspects of quantum electrodynamics, the theory of how electrons interact with light, we were getting results that matched experiment to absurd precision. Fine structure, constant calculations to 8 significant figures. Anomalous magnetic moment of the electron. The theory was working brilliantly, and at the same time there was this nagging thing at the edges, infinities popping up in the calculations. Numbers that should be finite coming out infinite, and then being made finite by a mathematical procedure called renormalization that involved, I have to be honest with you, a certain amount of sleight of hand. The procedure worked. The predictions were right, but it wasn't fully satisfying because the infinities were pointing at something we didn't understand about the theory at very small scales. And I spent a lot of time trying to figure out what that something was. I never fully solved it. Quantum gravity, the unification of quantum mechanics with general relativity, remains unsolved today. The mathematics at the Planck scale, where quantum effects and gravitational effects are equally important, is territory we have not yet mapped. I could have pretended this wasn't a problem. I could have said, look, the theory works, don't worry about the infinities, they go away in the end. Some people did say that, but I couldn't be comfortable with a fudge, even a fudge that worked, because a fudge that works is telling you something. It's telling you that your theory is an approximation of something deeper, and the fudge is the place where the approximation is breaking down. Physics has been doing this for a long time. Newton's mechanics was a perfect, gorgeous theory. It predicted planetary orbits, tides, projectile motion, the shape of the Earth. And then at the end of the 19th century, tiny discrepancies started to appear. The orbit of Mercury precessed very slightly faster than Newton's theory predicted, by about 43 arc-seconds per century, a tiny, tiny deviation. It took 250 years to notice it. And that tiny deviation led directly to Einstein's general relativity, which revised our entire understanding of space and time. A small error, a huge discovery. The imprecision was the clue. This is why I think the inability to achieve perfect accuracy is not just a limitation to be lamented, but a signpost pointing toward deeper physics. When your measurements don't agree with your theory to the last decimal place, you have two options. You can throw away the measurement, or you can take the discrepancy seriously. Science advances by taking the discrepancy seriously. The history of physics is in large part a history of following up on things that didn't quite fit. Now I want to come back to our alien civilization one more time, because I've been using them as a kind of thought experiment throughout this talk, and I want to squeeze the last bit of juice out of it. Suppose these aliens have been around for 1 billion years. They've had 1 billion years to develop science, mathematics, technology. Their physics is complete, or as complete as physics can be, in the sense that they know all the fundamental laws. They know quantum mechanics, quantum gravity, whatever the final unified theory looks like. They know it all. What can they predict? They can predict everything that is, in principle, predictable. The large-scale structure of the universe, the statistical behavior of quantum systems, the thermodynamic equilibria of complex systems, the evolution of stars, the formation of planets. They can predict all of this with stunning precision, but they cannot tell you where a specific electron in a specific hydrogen atom will be measured to be 1 second from now. They cannot predict when a specific radioactive nucleus will decay. They cannot predict exactly what quantum fluctuation in the early universe seeded the particular galaxy cluster that contains their home star. These things are irreducibly random, and no amount of intelligence resolves that. And here is what I think is the deepest and strangest implication of all this. The universe's refusal to be perfectly predictable is not a bug. It's built into the structure of quantum mechanics at a level that suggests it's not a feature you could remove while keeping the rest of physics intact. The uncertainty principle isn't bolted on from outside. It's a consequence of the wave-like nature of matter, which is a consequence of the quantum fields that are the actual fundamental stuff of reality, which means that a universe without uncertainty would be a universe without particles, without atoms, without chemistry, without stars, without life. If electrons had perfectly definite positions and momenta simultaneously, there would be no wave functions, no quantum interference, no exclusion principle, and atoms would not be stable. An electron in a precisely defined orbit would radiate energy continuously and spiral into the nucleus in about 10 to the minus 11 seconds. Every atom, all of them, instantly. The uncertainty principle is why matter holds together. It's why you exist. The inability to perfectly predict the electron is the same inability that prevents the electron from collapsing, which is the same inability that creates stable orbitals, which is the same mathematical structure that allows complex molecules, which is the same physics that allows the chemistry of life. So the next time someone tells you that the limitations of physics are frustrating, that it's a shame we can never achieve perfect prediction, you can tell them perfect prediction would require a different universe. And in that universe, there would be nobody to do the predicting. I don't know whether our alien civilization, 1 billion years old and brilliant beyond our imagination, would find this comforting or maddening. But I suspect they would find it the same way I find it. Wonderful. Genuinely, profoundly wonderful. Not in a watered-down, poetic sense. In the precise sense that it fills you with wonder, the sense that the universe is so much stranger and so much richer than the tidy clockwork picture we started with, and that the strangeness is not a flaw, but the very source of everything that makes the universe worth understanding. There's something I want to leave you with, a question more than a conclusion. We talk about the limits of knowledge as if they are walls that close us in. But every limit I've described to you today, chaos, quantum uncertainty, computational irreducibility, every single one of them marks the boundary of a territory that was discovered. Somebody had to go to the edge and find it. And the people who found those edges were not stopped by them, they were energized by them. Heisenberg did not discover the uncertainty principle and retire in despair. He discovered it and wrote one of the most productive periods in the history of physics. Poincaré discovered chaos and opened a field that didn't fully blossom until computers were invented 60 years later. Bell discovered his inequality and gave us a way to test the foundations of reality with experiments. The limits are not the end of the road, they are the beginning of the next road. And the aliens with their billion-year civilization, if they are wise, and I like to think that wisdom is what 1 billion years of science produces, they are not frustrated by uncertainty. They are at home in it. They have learned what I am trying to convince you of tonight, that the inability to know everything is not a failure of intelligence. It is the fundamental texture of a universe rich enough to be interesting. The question I want to drive home with you is this. If the universe, at its most fundamental level, is irreducibly probabilistic, if even the laws of nature are, at bottom, laws about what can and cannot be known, rather than laws about what exactly is it that physics is describing? Is it the universe as it is, or is it the universe as it can be known? Is there even a difference? I have thought about that question for a long time. I do not have a satisfying answer. But I think it is one of the most important questions in all of science, and I think it is a question that will still be worth asking when our civilization, if it's lucky, has been around for 1 billion years of its own. Go home and think about it.